Hey guys, and welcome to the first live tutorial of Computing Fundamentals. So today we have so many interesting things to do, and I wish you will enjoy this tutorial. So the first thing I will do is basically to start talking about the interface. So basically I'm going to use for today Jupyter, the interface that most of you are using, and this is the most close one to iCloud or to the SageMath on the cloud. Now, to use SageMath and to draw a graph, and to use SageMath for evaluating a graph attributes, and to learn how to use Sage to prove a concept is the main aim of this online tutorial. So I have a lab sheet for you if you want to see it. And this lab sheet is explaining exactly what we are going to do today. Now, be careful because I'm going to do most of the needed stuff for today, but you have to do something about those needed tutorials. So the first thing I will do is to start with Sage. So now I am in Sage, and if you go to the main page, you will be able to create a new project. You should be able to see now my screen, guys. Is the voice is okay? If it's not, just let me know. You must see now everything, guys. I am in Jupyter in SageMath. If not, please write this on the chat. Okay, all fine. So to start with Sage, the first thing we will do is to review the interface. As you know that we have the Jupyter interface, and the Jupyter interface has like this button for running, and this is for stop, and so on. So the most important thing is we have to create a new file. When I say a notebook, it should be SageMath 8.0. If you want to do Python 2 or IPython, it's up to you. But the most important thing is to use the same file that I am using. So from this menu here, just to create a new and select SageMath 8, and this will take you to this screen. Now this is the same with CoCalc and with other interface. If you prefer to use the notebook interface as I do, okay, feel free, and the difference is not really going to be much between both of them. However, the lab sheet that I have for you today explain a step-by-step, and I will make this lab sheet available for you guys in the classroom page during the tutorial, because there is few tasks that I want you to do. Now back to the main thing, and I create a new file with the name live tutorial 1. Now you must by now all know how to use or to install SageMath in VirtualBox, or you do it using the cloud. If not, you need to watch the video available in this channel, and you will find a full information about it. So you are free to select the one that better suits you. However, Sage Cloud is a little bit slow, so I won't be able to do this tutorial in it. So I will do the tutorial using my VirtualBox and using Jupyter interface. So the first thing is to run the VM and you wait for it to load, then go to your machine browser and type localhost at port 8888 or check the configurations based on the video available in this channel. My recommendation is to use SageMath with notebook interface. I find it really useful, and running it using VirtualBox image is perfect. However, for today, I will use Jupyter. There is another video I recorded using notebook, so feel free to find this video in the channel if you like to see how the notebook interface looks like. So once you have Sage, and I believe all of you have Sage now, and you can access it by now, so you can interact with me and you can do the same things as I do. Okay? Now we are good to start. If you have a problem, let me know in the chat box. I think I could be able to pause and to help and repeat. Seems to be everybody's fine, so I will start doing the graph theory inside Sage. If you are not sure what to type in SageMath and you would like to find out how Sage interact with a graph theory, all you need to do is to type a command to give you a help. Now in Sage, inside Sage, now type graphs question mark and then press the running command. That will give you loads of help about Sage. It will give you all the available method inside it, and you should be able to deal with Sage using the help available. So here you can see sometimes it's just give you the definition using another window, as you can see here, and you can read the full help available about the graph as an object, what kind of arguments it takes, and what basically we mean by vertices, and the property and the argument. And if you navigate to the end, you will see loads of examples about Sage, how you can basically use a graph theory inside Sage. So all you need to do is to copy and paste those examples. Now if you are using notebook interface, it works in the other way. You just type graphs, you open the left parenthesis and you press the tab key, and this should display the help. But it's not really it's not really big difference. So those information, it's for you to read later on or while you are doing the lab or the tutorials, and it will give you many examples about how you could create a graph. Now this is really nice. All we need to do is to use the magic copy and paste and try those examples out, and that will be really, really helpful. As you know, we have a graph, and this graph we call it complete graph. Now how I can create a complete graph in Sage? Now let me close this. Okay, it is Sage worksheet. So now I will create my first complete graph. Now put dot and type C and then press tab. This should give you loads of available methods. So I will create a complete graph, and this graph is basically with 5 nodes. So I need to know exactly how I can deal with the help. If not, you just basically write a question mark and then press on the running command. This will give you the definition of complete graph in Sage with examples as well. Now we know that a complete graph could take the number of vertices, and you can see this, what exactly it will take. So the signature of this method is to take n, and n basically refers to the number of nodes. Now this will be complete graph of 5, and I just press run. this will display now a complete graph for me. Another feature in Sage, if you want to deal with it as a Python and you define everything as a variable, you could just say K5, and in a new cell here, you just type K5 dot, and then you press the tab key to see all the available method, or you write show. This will basically define that I have to run this first, and then should be fine. K5.show. Now K5 variable has been defined, so I could deal with it as basically a variable. Now there is another method available for you to use, which is very interesting and nice. If you type K5.show 3D and you press run there, will display Sage as a 3D model. You have to wait for a little bit, and this feature works in Internet Explorer and Safari. I am not too sure about Firefox. I am not too sure about, definitely it's not running in Chrome. Now this is the 3D definition of, or the 3D structure of a complete graph in Sage. Now you can zoom in and you can zoom out in this object, and you can navigate it. If you want, for example, to animate it, you just pass this method, spin equal true, and then you run again, and this will create the 3D graph with animation. It will be animated. So now the complete graph is showing and it is animated. And there is so many options you can find to use this 3D feature of Sage. So this is a complete graph, K5 with 5 vertices, and you can show it using the method show, or you can just type one single command. But by the way, you can just type graph complete graph dot show, and this is also will display it in a 3D. So you don't need to you can make it whether one line, or you can just make it different lines based on the need. For the 3D object, once you right click on it, you can have different type of options to zoom, to animate, to change the structure. But I find this feature work, this right drop down menu is really working in notebook interface, but not in Jupyter. I think this is one of the few difference between both of them. Now there is another type of a graph. It's called Peterson graph. So if I want to define or to find out what a Peterson graph look like, I just type P and I select it here from the menu, which is Peterson. For the 3D, just a quick note, by the way, you have to have a JRE installed, or JDK should be installed in your computer in order to find out. Now, what I need to do with this complete graph, if I need to seek to exactly read the help available, and I will just, it's a question mark, sorry. I need to find out what this graph takes, what kind of object it is, what it returns for me. I find that this graph has no parameters, no argument, so I just call it, and this will create a Peterson graph for me. So I close this, and I will just do now semicolon p.show. And now I got the Peterson graph. If you want it in a 3D, just change this method to 3D and you should be able to see it in a 3D. Okay, I have somebody telling me that the 3D of Sage is working in Chrome, so this is a perfect news to know. So now I have the Peterson graph created in Sage. You will find this 3D thing may be useful when you try to do the isomorphism and comparing two graphs together. Guys, do you have any question before I move to the next thing? If not, I will go quickly to the cloud, to that strange website cocalc.com, just to give you a little tour, a quick tour about it and how it's a little bit different. So if you are using the cloud, you will find that you have to create a project, and then inside the project you will be able to create new files. I find IPython workbook is fine, but I prefer to use the one with Sage for it, which is the Sage worksheet. So if you open this object, it will tell you exactly, it will give you the same interface as Jupyter. I was creating thing and navigating because the commands are not the same between Jupyter and Notebook. From the drop-down menu in the cloud, you can find few information like graph.tab, and this will generate an object, a graph for you. Now the same, if you want to create a complete graph, you have to type C, and this will complete the command for you. So this is complete a graph selected, and this is 4 this time, and I will do immediately the show command just in case to display it. So this is a complete graph with 4 vertices. They support as well 3D plotting and 2D, so you can use it, but it's not really perfect, similar to Notebook or Jupyter. It's a little bit not perfect, and you have to customize it and tweak it, and I haven't really tried to fix that. Yeah, so you can see the 3D here, and it's supposed to be okay, but I think they have to install a specific plugin in the server in order to display or support 3D. So that's all you need to know about the cloud. It's the same. So most commands except the help and the 3D will work in any interface, whether you are in Notebook interface, in Jupyter, or in cocalc.com interface. So I back again now to my worksheet, the Sage worksheet. I was working on it before. Guys, any question before I carry on? All good? Okay, so let me go back now to the classical one used by the majority of you, and now we will start to create different type of a graph. What about a cube graph? We discussed in the class that there is something called a cube graph, so I will make something called C, and then I will go graphs dot C capital and tab. I should be able to see something called a cube graph. Now I have a cube graph. Now let me pass number 4 to this, or if I need to get the help and study what this complete graph do as an object, this is return a hypercube in n dimensions. So the n here is not basically the number of vertices, it's something else. It is the bit string as we described in the lecture for connecting those graphs. So if we say, for example, graph of 2, and then I do c.show and I run that, this is how a complete graph look like. It is the bit string. So 0, 1, 1, 1 is the name of the vertices, and it's link them based on the bit string. If you want to change this to 4 and run it again, it will display different type of cube graph. If you would like to see this in a 3D, all you need to do is just to add a 3D there, and you wait for a few seconds to see the 3D object of this graph. So here I have now the 3D of a cube graph of 4. And as I said before, the cube graph is used in the CPUs now. They have small little CPUs, as you can see in those nodes, and they are connected with each other. And this is the mean of quad core and dual core and so on. Because we have many, like 8, 16 CPU connected with each other, so they can act like a single core as a single CPU, and they deal with the program or with the process in parallel. Excellent. So everything is fine for everybody. The only problem I find with the 3D, it's look like you like it. In Jupyter, when you click here, this menu is not active. But I could show you in Notebook later on if you want. Just right click in it and make spin on, spin off. It will be easy to work with. So this drop down menu in Notebook is working perfectly. I don't know why it's not in Jupyter. But this is just only something to help us with visualization. Now we need to start doing some work. So I will start creating a graph object. So the graph object in Sage is represented with no loops or multiple edges, and you can basically add a weighted graph for those edges. Graph object takes the following input. It takes the data, and this is can be any of the following, or you can just create something like G equal a graph, and you pass an empty parameter to it. So this will create an empty graph. Also Sage has an empty graph. So if I want to create empty graph, this is a graph, empty, press now the tab key, select empty, even not selection is good. And this is a graph, an empty graph in Sage. Now, if you want to check that G equal E, or just type G equal E in Sage, and it should return the result of comparison for you. Yes, true, both are empty graph. So the special type empty graph is equal to an empty graph of 0 vertices. Now, if I want, for example, to create, let's say, a graph with 5 nodes, I will just specify here that I need 5 nodes. And then I just do semicolon G just to write the same command in one single line. And this will display the graph G for me. Also, Sage gives me the ability to add vertices. So if you click G dot add and then tab and you select vertex, this will add a new vertex to the graph that we just created in the previous step. Now I have a graph and I have 6 nodes in it. Sage also could help in adding an edge. So you can add an edge, and now I would decide to add an edge between 0 and 1. semicolon, G just to display the graph. This is now make the first edge, the first connection between 0 and 1. I could repeat the same thing, or I could do another thing, which is add edges. There is another method which is basically going to add another edges for me in this graph, and so on. So now we know by now how we can create a graph object, how we can add a vertex, and how we can add an edge to the graph. If you have any question about this, guys, please post it in the chatter box, or I will carry on with the next part of this tutorial. Seems to be we are all good, so I will carry on, and the next thing I will do, maybe I just show you how you can print vertices. So if I call j dot vertices, I call this method, and whether you do like print before it as a Python statement or you just leave it as it is, both are going to work in the same way. And this is will print the vertices participating in this graph. In the same way, if you want to print all edges in the graph, just do G, and this is edges, select edges, call the edges method, and run the cell. This is will print basically the 0, 1 edges that I just created. Now the none here in the edge is basically the label, the name of the edge, and we will know how we can specify the name of the label in SageMath. I could, for example, add another edge between 2 and 3. Put in G and then display. So now I have added another edge. Now, what about adding many edges at the same time? Is there a method for that? Yes, there is a method for that in Sage. So all you need to do is now to go and type the following command. So G dot add edges now. Now to specify an edge, you have to pass them as a Python dictionary, where the element of this Python dictionary is going to be a subset. So here I'm going to say that I have an edge from 3 to 4, and in comma I have another edge going from 4 to 6, and I have another edge going from 6 to, I have to create a subset, so don't forget that, 6 to 0. Now this should create and add edges to the graph in the above. Now we have created this graph, and this graph is called basically a cycle. So this is how we can add multi-edges in the vertices. Again, now at this stage, you can just simply say G dot edges, and you select the method edges, and this is will print the number of the edges attached to this graph. Yes, a Python list, yes, not a dictionary, Joseph, yes. So we know now how we can get all the vertices in the graph, how to get a list of all edges in the graph, and how we can add an edge and how we can add a vertex to the graph. By this stage you should be able to do that. If not, just let me know. So before I start with the second example. Okay. Now, what if I want to create a graph specifically? Like I want a graph to be well defined based on a diagram. For example, I give you a diagram, and this diagram saying is basically we have a graph, and this graph has a vertex, and this vertex is going now to the list 2, 3, 4, 5, 6, and 7. How this graph will look like. Now just type G and then run the command. It will display, that's the small g graph, not the capital G. So you have to be careful. Capital G is not the same as small g. So this is a graph with 8 vertices created where 0 is the center for this graph. Another example, I want to clearly define, for example, G2, and G2 is a graph object where I give the specific relationship between the vertex 0 and this vertex 0 going to 1 and 2. So these both are vertices. Now, comma, I will specify the relationship of 1, and 1 is going to 2 and 3. Let's say 1 is going to 1. This is self loop. I don't need to include it here. And we will see now how you can create undirected graph using Sage. Now 2 is going to 3, and this is my graph, how it's look like. Now type here G2 and run the command. You should be able to see this graph. So 0 going from 0 to 1 and from 0 to 2. Now the second thing we have, which is 1, is 1 going to 2 to vertex 2 and to vertex 3, and 2 is going to vertex 3. Now maybe somebody will say, well, 2 is also going to 0. Why you don't include it? Because 2 have been covered by this definition here, by this relationship. I don't need to repeat it because the edge 0 to 2 or 2 to 0 are the same in undirected graph, or in simple graph the direction is not important. So it's not an ordered list of objects. Okay guys, all good? If I'm going so fast, let me know so I can slow down. We have 1 hour and we have plenty of time to spend in this. So I'm assuming you are in the same step that basically I just did. So you have created a G2 and you draw this graph as explained in the video. Now the next challenge for us, if we want to build a graph and we give each edge a name, how we can do this? To do such thing, basically in Sage, we want to define the label, and I show you how we will do that. Now this is I will call it named G, just to distinguish between the others that we just created. That's graph. And this graph has now 0 vertex, and this zero vertex is going to 1. And the name of this edge is single quote X. Now this has been finished, so I could do now another relationship between vertex 0 and another vertex, let's say 2, and 2 is called Z. Now comma, also the vertex 0 is going to 3, and the 3 has the name of its edge A. I finished now all the relationship with vertex 0, so I should be able to exit now this list, and I start another relationship between 2, and 2 is going to 5, and 5 is the edge 5 between 2 and 5 is called something here. First I put G, not name G. Okay. The second thing, you notice that the labels has not been shown here in the diagram. To show the label, you have to tell Sage specifically to do so in the show method. So in the show method, you need to say edge labels equal true. As you can see now, I have the edge labels showing at each edge after I call the method show, and I pass the parameter edge labels equal true. I can pause it now. Just give me a few seconds. I will be able to do that. You mean the lab sheet? The only reason I don't want to post it before the tutorial, because I want to see you all here in the lab, so in the live tutorial. It's very important for us to decide whether this type of labs are really useful or they are not useful at all. So if you go now to the classroom page for this course, you will find that lab 2 on the graph theory has been uploaded in the same link where I put the announcement of the live tutorial. Can you see it, guys? Okay, good. Now there is one thing we want to do now. Back to this graph, we just managed to make the labels appearing in the show method. Now what if I want to change this label here between the vertex 0 and the vertex 2? What I should do? Is there any way I could basically change this name? Well, there is. And you can do this very, very quickly. All you need to do is to go back to that graph, which is named G, and then you do add edge, and in the add edge method, we can change it by specifying the same set of vertices. Okay, So for example, I could just make it look like this. To, for example, VT249, semicolon, just type named G and then run the cell. You should be able to see label is a typo. Should be able to see now the new name with this. After you do the same trick, which is named G, would show edge labels equals to true. Okay, labels. I copy this now. I don't know what's happening, but now this label has been changed because basically the vertex 0, 2 or the edge is basically not duplicate, it's a unique name. So adding the edge with a label is going to be acting like renaming the edge. Now let's start doing some real business with those graph. It's not enough for us just to draw, represent those graph, add labels, add an edge, add a vertex. We need something more. Like for example, how we can find out the degree of a vertex. How you can do this. So we know the degree of the vertex 0 is basically 3 in this example, right? Can we verify this? Yes. We can just type named G dot the method degree. Now what this method do? Question mark if you are not sure. And this will give you basically the n plus out of the diagraph if this is a diagraph, or it will be giving you the total degree. A diagraph means directed of the graph. And which vertex we want to calculate the degree for? It's number 0. So we have to just put 0 there and we will calculate it. So the degree of 0 is 3, which is correct. This is 1, 2, and 3. Let's say we want to calculate the degree of the vertex 5. The same method, if I type it correctly, this should be named G, sorry. I should maybe next time use a much easier variable name so I don't do mistypo. Okay, and now this is displaying the degree of the vertex 5. What else, guys, we could find out? What else we could basically, or what else we need to know about a graph? Do you remember the neighborhood relationship that we defined in the second class? Is it possible to use Sage for displaying the neighborhood of a vertex? Can we understand or find out the neighborhood of a vertex in Sage? Yes, we can. And that's in the same fashion. We just do named G dot neighbor, and you will find there is neighbor iterator and there is neighbors method, which is the one I'm going to use now. And neighbors, I want just to see who is the neighbor of the vertex 0, and I run the method. We will check now if there is a path, if there is a circuit. All these methods are already supported in Sage. Now this prints for me the neighbors of the vertex 0, and they are 1, 2, and 3. And that's true. If you look to the diagram here, 0 is neighbored by 1, 3, and 2. The second thing, or one of the issue we had before, like we discussed how we can represent the graphs using adjacency matrix and incidence matrix. Is it possible, for example, to print the adjacency matrix and the incidency matrix for this graph? Yes, we can. So named G dot adjacency matrix. It's here, the last method in the list. I call this method, and this is will create or will print out the adjacency matrix of this graph. So the vertex 0 to 0 is 0, the vertex 0 to 1 is 1, the vertex 0 to 3 is 1, and so on. Now the vertex 0 to 5 is basically 0 because there is no edge between 0 and 5. And if you don't understand the definition or how adjacency matrix is constructed, please try to work on this and try to understand it as much as you can. If you still have a problem, let me know, and we maybe by an email, maybe we can organize a few tutorial about adjacency matrix in the future. The second important type of graph representation is the incidency matrix. Is it supported? It is incidency matrix. I call this method, I run the cell, and this is will print the incidency matrix between the vertices in this graph. So up to this point, we know how to add vertex to display vertices. We can add an edge, display them, or add multiple edges at the same time, and we can print the incidency matrix and the adjacency matrix and the degree and the neighborhood of each vertex. Now another type of a graph is called diagraph. How we can represent it in Sage. Now this method I find a little bit different from or between different Sage interfaces, but I will try to put it as it is. So I will do now diagraph. This syntax should work in Notebook and in Jupyter. I am not too sure about the cloud. So a vertex 1 is going to 2, 3, and 4. Okay. Now the same relationship between 1, 2, 3, and 4, we have another relation between 3, and 3 is going only to 4, and we want to see how this matrix, this graph look like. So yes, it's working. So this is a directed graph where 1, there is a path from 1 to 2, and from 1 to 3, and from 1 to 4. You can call this, for example, D as a variable. Make sure to run it so that the variable is compiled and Sage could understand what you are talking about. You can show it in 3D if you like to see how it looks like. Wait for a few seconds and it should be able to see the graph. So this is my diagraph in 3D. You can spin it, zoom in, zoom out. It's very nice to see. Now you see now all edges has like some arrow on them, just to explain that these are directed edges, not undirected edges. Another example about diagraph could be like this. I have a diagraph, and this diagraph is basically from vertex 1, and now we have labels in those vertices. So 1 is going to 2, and this is called A1 and A2. So there is multi-path between 1 and 2, and we have 3, and the 3 is going to B, and the 3 also going to 2, and the name of the path is D. Type this in and press D to see this type of a graph. So this is another multi-graph where we have multi-edges involved between 1 and 2. Okay, So this is how we represent diagraph. Now if you want to show the edges, the same trick again, show edges, labels equal true, and run this method to show the label. Now this is A1 and A2, and this is B and this is C. So these the edges I just construct using the definition above. For diagraphs, we have different, we can check the neighborhood of a vertex, but it's not going to be a very accurate relationship. So how we can, for example, display the diagraph, the neighborhood for a vertex in a graph showing here, for graph D. D dot neighbor, and neighbor should be neighbors first, and I want the one for the vertex. So the neighbors of 1 are 2 and 3. Maybe if you add later on a loop, add an edge between 1 and 1 and check, or I will add that. Just wait. Add edge between 1 and 1, and I forget the syntax, so let me go back, how we could do the labels. Yeah, comma, label equal something. So I could now go comma, label equal, for example, loop. Okay, so this graph, when I define it, I should specify that it takes loops. I will come back to this later on, so ignore this fact. Now if I want to check all the edges in iterator, like I want to print, for example, all the edges between 1 and 2, I could, or the neighborhood, I could simply do a for loop for a and d dot neighbor out iterator, and let me check that out is going to 1, so this is will be with the graph 1, and basically this is a classical Python loop, and then I run. So this is now print a, 2 and 3 are the neighbor. The same could be in instead of out, and we have nobody coming to 1, so there is no neighbor to 1. But if you change the vertex to 2, you will find there is so many vertices are neighbored, because we have many paths coming to 2, so we have the neighbor 1 and the neighbor 3. As you can see now, the diagraph is basically different when you deal with diagraph. The edges are different, the neighborhood is different, and the degree of the vertex is also different. If you have a question, please guys post it before I move to the last bit of this tutorial. Are you there guys, or you left already? Okay, now I will do now the, maybe you should be able to do it as well, but if not, just let me know. Just for curiosity, I want to be able to print the degree of the vertex, which one, 2, in this graph. So the degree of vertex 2 is a 3, and that's basically what I can see here in vertex 2. Also, there is degree in and degree out, so you can check both of them. So if you want to print only the degree of the vertex, you just type degree and the number of the vertex. That's the degree of 1. Now, just to make sure we have understand what we are doing in this, I want you to be able, just quickly now in 5 to 10 minutes, take 10 minutes guys to do the following. I want you to draw a complete graph called C. You can specify the number of vertices, and then I want you to draw a line graph. Look for a line graph in Sage. Maybe look for a path, because path and line are basically the same. I want you to draw an empty graph, and I want you to represent the graph L similar to the following figure that you can see now in the screen. Okay guys, well done for doing this task. It was very fast to do it in this time. I have to admit that. Now I want to show you a few things. Basically, I want you to go back to the loop, because loop is very important issue in Sage. So if you have this graph here and you define it, the first definition you did here, you don't specify loops true. So to do so, you have to, I show you in a new example. You have to say, for example, this is D equals Diagraph, and this Diagraph is going from 1 to 2 and so on, and then you specify that loops are true. Same also apply to multi-edges if you want to have multi-edges. Now I could simply now say D add an edge, and this edge I want you to go from 1 to 1, label equal loop, and then I will display D dot show. Then I have to pass edge labels equal true, and then you have to run this in order to see the loop now with the label on them. So now you can basically do a loop inside Sage with a Diagraph. However, there is many methods for loops, so you have to be careful when to use them. So for example, if you say D has loops, you call this method and you do run, it's true, and D allows loops, and then you press run. Now the first one is giving me 3 because basically loops already defined in the graph definition, in the basic constructor of that object. We have loops allowed, and we will see later on how to deal with loop, where we need to be a little bit careful because loops are different, how Sage is going to deal with them. If you want to print the loop exists in the Diagraph, you need to call the method d.loops and then run that command. It will give you that I have a loop between 1 to 1 and loop 2. In the same scenario, you can just simply add another edge for another vertex, and in this case I will add it to vertex 3 and 3, and I will call this loop 2 for example, and I just do now show edge labels equal true to make sure that I can see the result of my modification. So this is what I want to say about loops, and by this we should be able now to define a graph in SageMath. We should be able to add vertices, we should be able to add an edge, we should be able to add edges, and we should also be able to print adjacency and incidency matrices. At any time during your work, you could basically press tab or the question mark based on the interface, and you should be familiar with this by now, to complete the tutorial and any other type of tasks that you will be given. Quick one, you managed to draw a line graph, right? So who wants to tell me how you can draw a line graph, just to make sure that you did everything, or you find how a line graph is represented in Sage? Anyone, guys? If you do graphs L and then you press tab just to see what's the methods available in Sage, you will have no line graph specified. You have a ladder graph. So what's a ladder graph look like? I just simply do this just to show you how a ladder graph look like, which is basically a ladder. Now what you can in Sage is drawing a path. A path graph of, let's say, 3 vertices. So this is a path graph, or it is a line graph. So path graph in Sage is basically called line graph, or line graph is called path graph. So the last thing I want you to do for today is another task, and this task you can do it later on after you can see this video. The video will be available on the channel, so anytime. You don't need to send them to me. You just do them for practicing, for your own knowledge. If you find yourself stuck at any stage preventing you from doing the lab, the video will be available on the channel. Feel free to go back, see it, watch it, and enjoy it. And don't forget to give, if you like this tutorial, just press the like button below just to make sure I understand that you prefer this method or you want me to do a recorded tutorial or something else. If you don't like it, thumb down, that's fine, it's your opinion. Thank you guys for joining me in this tutorial. I hope it was really useful for you. I will see you next week in the lab, and enjoy the rest of the day.